Hello, everybody. I am going to run through the syllabus for the course Remote Sensing, GPS Applications, and GIS with Lab, just to contextualize the information and to provide a little bit more detail, help you understand things. Let's see. Kind of top matter up here, name of the course registration number, department, program. The course is, of course, being offered online, but if you, in addition or instead of using the virtual desktops that AUM has equipped for you, you may make use of the physical space, the Geospatial Research Lab, room 310, TW. My name, Dr. Nick Cuba, Assistant Professor GIS, my first semester here at AUM. Office hours, be holding office hours Tuesdays and Thursdays from between 11 and 1. And I've listed my office, but these office hours will be held over Zoom. I'll create Zoom. I need to create an AUM Zoom account and then a kind of recurring meeting. We'll link this on Blackboard. Feel free to drop in during those hours on those days whenever. If you have any other issue that needs to come up, please don't hesitate and just email me here at ncuba@aum.edu. Required text for the course, just one book by Chuvieko, Fundamentals of Satellite Remote Sensing, CRC Press. Here it was signed the second edition, came out in 2016. And here's the ISBN number if you need to find it. So this is an update, same textbook, updated version compared to the last time the course was taught. Um, One thing to note here, the second edition is assigned. There is now a third edition, just came out a few months ago. Um, I haven't had time to review the third edition. I don't know if it's kind of if it's worth the upgrade. I mean, remote sensing things. It's a field that's developing. It's in progress. Things come out, but it had been more than 4 years between the first and second edition. Put it that way. And I do like the second edition. So if you want to purchase a third edition, the most recent, which you might, it's good to have these books as a reference um, going forward. And maybe, if you don't, if you think it's worth the premium, feel free to buy that third edition and I'll help you figure out any kind of page number differences, something like that. But the second edition is kind of what the page number is, what all the course will be in reference to. There will be additional readings beyond those from the Chuvieko book. Those will be things that I'll copy, I'll post up on Blackboard, so you don't have to worry about getting them yourself. Basic course description, kind of the premise here. It's remote sensing is a set of techniques for observing objects at a distance. It's become an extremely important component of spatial technology, widely used by scientists, governments, and business. Overall objective of the class is to provide students with a theoretical background as well as practical experience in applying remote sensing for observing and evaluating the Earth's physical environments. So here, kind of the big theme to capture is the need to balance the theoretical background with a practical experience in application. So to do that, course has lectures, demos, and lab exercises using a few different types of data. So here mentions aerial photos, remotely sensed data from a variety of platforms. So some of those could be observing the way in which surface materials reflect sunlight in different ways. Others can be observing the speed it takes for light emitted by a sensor to return to that sensor, and how that kind of information can help us characterize the surface. So here, as I said, you'll need to balance learning the general models and laws through which inferences can be drawn through remote sensing, this being kind of the theoretical aspect, as well as the very specific and historical paths through which observation systems have come to exist and operate. So that's something that's a little bit different from the need for hands-on experience using software applications or field techniques. This is kind of the fact that for a long time, sophisticated observation systems required budgets and really yielded economic models that only public institutions could underwrite. So you see kind of USGS, NOAA, NASA programs. Now you do see a lot more commercial data providers getting in the game, and we will touch on that. But remote sensing, kind of as a community of practice, is something that people do, has been done in certain ways, and this kind of it's we're set on a path, and kind of how things have been done influence how they are done, how they will be done, how they can possibly be done. And then specifically in terms of skills, intent of the course to improve your ability to interpret aerial photos, uh, both in a visual sense, kind of looking at it, but also learning about computer abilities to enhance those photos. Ooh, must have heard me. Zoomed in, enhance. There we go. As for specific applications, we're going to be working in Envy as well as the Esri application. So ArcGIS for desktop, Arc Pro. Envy is kind of a remote sensing industry standard application um, for kind of image analysis, deriving variables, that sort of thing. And so I'll be updating quite a few labs to Envy that we'll be working on. But remote sensing is it's such a vital component of any kind of spatial analysis that Esri has long had raster data analysis capabilities programmed in, but even more recently they've expanded this. So it's worthwhile to learn how to take advantage of those capabilities so that you can maybe more easily work in analysis of remotely sensed data to the rest of your spatial workflows, which tend to be in Esri products. So we'll have um, a little bit in Envy, a little bit in ArcGIS and ArcPro. So this kind of material will be learned through semi-weekly laboratory exercises, so that you do get that hands-on experience. Those laboratory exercises will account for about almost half your grade, 45%, about 5% per exercise if we have 9 of them. We will have exams. These will count for less, but they will count for, a non-trivial portion of your grade. There will be a final project in this course and also kind of a borderline participation grade, just for some of the collaborative or public group activities we do. So I mentioned attendance here. Of course, it's an online course. I just kept that section in the syllabus to emphasize the need for maintained attention and work on these things. It's a lot of the knowledge in any given week builds on what came in the weeks before. So if you skip, if you miss one of those weeks, say, for a period of time, um, getting caught up can be a little bit difficult. If you have any kind of conditions that make your learning in this class more difficult, you have institutional resources that you can work through, and they're listed here in the syllabus. You can also come to me, and we can find a way to kind of hit on your own learning outcomes in the course, if that's something that you're interested in. Some kind of standard language on non-resigning classes, academic dishonesty, steer away from. Tips on how to do well in the course. One is to spend time on the lab exercises frequently. Now, maybe that's not the clearest um, language to use there. What I mean is spread the work out over multiple days rather than trying to do everything in one large block of time, even if it's the same amount of overall time you spend on the assignments. This is because some of the kind of software application work can it can hide some kind of pitfalls, trivial, not very important um, things that can could catch you up. So, for instance, you don't know what tool to use, or you don't know what parameter to input, and those are kind of questions that I can answer pretty quickly, but there's going to be some sort of communication time lag and you articulating a question to me reading it and getting an answer back to you. And so in this course, I'm going to aim for Friday as being the day when labs are distributed. Save this Friday, no lab in the first week. Those will be due a week later, the next Friday. My recommendation is to take a look at it at least that first day, spend a little bit more time on the weekend so that by Monday you can get any kind of questions that have been holding you up to me. Tip 2 is just reiterating, keep up with the coursework, um, pose questions if you have questions, make comments, think critically. Finally, work to develop your writing skills. So in some of the lab exercises, you're going to have to do some short writing to describe the products you generated, the inputs you used, and the operations performed. But also for the final project, you are going to have to do a little bit more substantial writing in a more organized fashion. So if that's something that comes naturally to you, then great. But if not, just keep it in mind that it's something to continually make progress on and to be aware of. Next, here the grade scale. So essentially, there are no minuses, no A minus, no B minus, C minus like that. There are B and C pluses. And for these, I've just listed out the kind of the numerical grades that correspond with the letter grades there. Email and Blackboard. Blackboard is going to be the main means of kind of material conveyance. So that's where you're going to find all the content for the course. It may have kind of ways that you can communicate me built into it, but just to ensure that I get back to you as soon as possible, email me at my AUM email account, ncube@aum.edu, if you need any issue. Here's a breakdown of the course evaluation, weekly exercises, midterm, final exam. Both will be take-home open book. Final research project, which we'll get into about halfway through the semester. We kind of have our good theoretical grounding and we're starting to learn about more and more sensor systems and data sources, data products that are out there. And then we'll have some time toward the end of the course when we really are able to dedicate quite a bit of effort to those projects. And finally, a little bit of participation in the grade, because although it is a fully online course, I am going to ask you to contribute to some shared resources via discussion forums on that course. Important dates, and then let's see, schedule of topics. And these, there are 11 listed here, including the final projects at the end. They don't exactly map onto weeks of the course. I think we are going to lose kind of half a week for Labor Day, and then we can see something like a topic 5 is really, I mean, that's kind of a 2-week lesson if you're trying to think about how to budget time. But this first week, we do not have a lab, just kind of a course introduction. We'll cover what is remote sensing and some of the basic vocabulary. For a reading in the Chuvieco book, just chapter 1, the introduction. And now if you're waiting on a physical copy to come through the mail of that book, you can go on Amazon and get a sample of that book, which includes the introduction. So I'd recommend you do that if you are waiting and you want to get that done. You'll have to maybe get the desktop Kindle app or something, but good product. You can read everything pretty clearly. Second topic, geodesy. Short review of that, kind of models of the Earth, and also get into physical model of energy matter interactions. A little bit on projection, scale, and coordinate systems, and modeling really the surface. And for that, chapter 2, physical principles of remote sensing. 3, a bit on the history. As I said, kind of things have happened in a certain way, and that influences how they are today. That have a somewhat longer chapter, Chivica, 50 plus pages. A little shorter next week, understanding light and electromagnetic waves. Here, furthering our understanding of the energy matter interactions that kind of allow remote sensing to be a reliable method for understanding physical systems. Next, here, kind of that really long topic here, visible light and thermal infrared sensors, air photo interpretation, and photogrammetry. This kind of these data products are maybe more easily interpreted by the human eye, kind of visually, than what we see in topic 6, these active sensors. It's also where a lot of my working background is, and I'd say the longer historical archives of data. So there's quite a lot of material to get through. It's a topic that's a beast of a topic, a little bit outsized compared to the others. After that, we'll get into active sensors. So visible light, what we're looking at is reflected sunlight, thermal being temperature emitted from objects, oftentimes have been absorbed sunlight previously. Active sensors, for instance, microwave, radar, and LiDAR, are sensors that generate energy themselves. That energy propagates from the sensor. It interacts with matter, and some portion will return to the sensor. So it's really measuring time, inferring distance, and then based on models of the Earth and the sensor, understanding kind of two-dimensional, three-dimensional space. But because of the electromagnetic components of, say, radar, more information, some may be non-intuitive, but definitely interesting, can be inferred about that. Typo there. We'll get into Landsat. This is being the kind of 35 plus year. I guess if you get into the multispectral scan sensor, you're looking even further back. A long-running USGS program to kind of document land cover on the surface of the Earth. That's kind of going to be a standalone topic, as will this high-resolution panchromatic color satellite imagery. Some of those sources are more recent and commercial providers. So we'd be able to kind of draw on techniques we learn in topic 5 onto kind of real actual data products as they exist. We'll then look at supervised and unsupervised classification. This is really a process of grouping different pixels in a remotely sensed image into a number of categories. And this can be useful for a number of different applications. One of the most significant is understanding land cover, kind of broadly characterizing materials within a scene. So we'll learn about quite a few different methods for that. And then finally, accuracy assessment, whether that's kind of positional accuracy of the features that you can resolve from remote sensing images, or category accuracy from the output of a classification. So there's kind of a chapter in the book on that. And then finally, we'll have more time to dedicate to our final projects. Below are just some notes on your lab exercises, kind of what naming conventions to use so that All data can be loaded by me to evaluate. And then just a few lines on final research projects, um, kind of about how to thoroughly document your work, be cognizant of your goals there. We'll get into those in much greater detail in a few weeks once we have the kind of the background um, in the theory and in data sources to kind of outline models and pursue those questions.